Hello. Right, we're asynchronous, week 7. Last night, whenever I last saw you, technically for me it was last night, we were talking about using the method of partial fractions to integrate. So we're going to continue doing that today. I'm going to show you a few different types of techniques that you're going to use with partial fractions, depending on what kind of different types of denominators you might see. So the first one I want to show you is for repeated linear factors. So this would be example 3. And I'm even going to label this just because I really want you to kind of see that there are these different types of problems you're going to be looking at. So this will be repeated linear factors. My focus a little better here. Worse, better, worse. I feel like I meant the eye doctor. Which one's better? Number 2, number 1. There we go. All right. This one will be in the numerator 6x plus 7, and in the denominator x plus 2 quantity squared. Okay, so right off the bat, this should not be a situation where you're looking at this something like this on a test and being like, oh my gosh, I have no idea what to do. You could technically, yeah, you might have back in Calc 1 said, oh, maybe I'll try a u substitution. But notice that if you let u be x plus 2, du is then dx. Well, you don't just have dx, you have 6x plus 7 dx. Technically, you could probably have worked this out in Calc 1 using some sort of method of splitting up this constant like we've done the last couple of days, just by splitting this into 2 integrals. But this is something you're going to do pretty easily with partial fractions. But notice that you have a repeated linear factor. Now, if you're not familiar with the terminology here, linear just means that your factor is, it just has x to the first power in it. So a quadratic would be if you had something like ax squared plus bx plus c. Linear is of the form, I don't know, ax plus b, something like that. So if it's a repeated linear factor, you're taking something that's in the form of ax plus b, in this case a would be 1, b would be 2, and you are taking it to a power. So I know some of you are looking at this and thinking, well, how's this linear? You're going to square it and it's going to become quadratic. The factor itself is linear. Yes, technically it becomes quadratic when you square it, but as a factored form, when it's factored, it's linear. So this would be an example of a repeated linear factor, and we have a special way that we work with these. When you set up your partial fractions, you're going to set this up on the left the way that you always would. You're going to take your integrand and set that on the left-hand side. But what you're going to do here is you're going to set up a over 1 factor of your denominator. And then b is going to be over both factors of your denominator. This is just the process that you're going to use anytime you have repeated linear factors. So you cover 1 factor using a and the other one using b. Now you're going to start to recognize here, and you're going to see more examples of this, that a and b are constants. Your numerators here with your partial fractions are always going to be 1 degree less than your denominators in their factored forms. So if your denominator is linear, your numerator is going to be a constant. And if you're just like, okay, well, what else could it possibly be? It's a and b. We're going to switch that up in another example here. But first, I'm showing you repeated linear factors. So you're going to use the same process here to clear the fractions. You're going to multiply both sides of the equation by x plus 2 quantity squared. If you would like me to write that out, I will, if maybe that happened too quickly for you in class yesterday. So every term gets multiplied by x plus 2 quantity squared, which is your LCD. And then you're just going to cancel where you can. So both of those factors are going to go. Only 1 factor of x plus 2 will go in that first term on the right-hand side. And the second term on the right-hand side, both factors of x plus 2 are going to cancel. So what that leaves you with on the left is 6x plus 7. On the right, you have a times x plus 2, and then you have b. Now, I would not distribute this in. For something that's very basic like this, we're just going to be letting x be this number or letting x be that number in order to find a and b. In the next example, I'm going to show you something more complicated that we're going to have to do to find a and b. But in this case, we're going to do two things. First, we'll let x be -2 because I know that -2 plus 2 is going to give me 0. And if I multiply a by 0, then I'll just get b and x. So I'll let x be -2. Then I'll have 6 times -2 plus 7 equals a times 0 plus b. -12 plus 7 is -5. Now I have b equals -5. So that's one quantity I needed. And now I just need to find a. Since we already know that b is -5, if I'm trying to solve for a, you can let x be any value you want just to try to get the value for a. So I don't know, for instance, you could say let x be 0. Well, 6 times 0 plus 7 is a times 0 plus 2 is 2. And I know that b is -5. So I'll just think of b as being plus -5, which is -5. 7 then is 2a minus 5. Add 5 on both sides, and you get 12 equals 2a, and a equals 6. Now that you have your values for a and b, go ahead and rewrite your integral using this form here on the right-hand side, a over x plus 2 plus b over x plus 2 quantity squared. Because remember, your integrand, this is before we canceled, is equal to this right-hand side. So we'll have 6 over x plus 2 plus b, which is going to be -5 over x plus 2 quantity squared dx. Now, for your first integral, you have just a natural log. You have du over u. If u is x plus 2, du is going to be dx. So you'll have 6 times the natural log of x plus 2. For the second integral, you have a u substitution again, but it's presented a little bit differently. So if you want, you can write this as -5 times the integral of dx over x plus 2 quantity squared, and then we'll just work on this integral separately, but this is a Calc 1 integral. So you're going to let u be x plus 2, du is dx, which is exactly what you have. So you'll have -5, and then the integral of u to the -2nd power, because we're moving that u up so that we can integrate, and then du. That guy's going to come down. You don't have to keep rewriting. Just, make sure it's rewritten at the end and make sure that you don't lose it. So I try to note it by drawing the arrow down so I don't forget to write it at the end. Increase your exponent by 1. So -2 plus 1 is -1, and divide by the new exponent. So your new exponent's -1, so you can just pop that u into the denominator. And then you can simplify. So we have 6 times the natural log of the absolute value of x plus 2. And then a negative times a negative is a positive. So you have +5 divided by our u, which was x plus 2, plus c. So that was an example of repeated linear factors. So we started here at the top, recognizing they had a linear factor, but to the 2nd power. When you set this up, you have 1 power and then both powers. So if you're wondering, well, what would happen if this was cubed instead of squared? Well, then you'd have a over x plus 2 plus b over x plus 2 squared plus c over x plus 2 cubed. So you could still do it. It would just be a little bit more tedious. Not the end of the world, though. We found a and b, and then we rewrote the integral, and then we just turned it into this Calc 1 integral. Okay, so let's do a combination here of these things. Get into the nittier grittier here. So this one is going to be example 4. And we are going to include a quadratic factor here. So not just repeated linear, but also a quadratic factor. The numerator is 4 minus 2x. The denominator is one factor of x squared plus 1, and then a factor of x minus 1, quantity squared dx. And then we'll do a repeated quadratic factor after that. Okay. Excellent. Wonderful. I thought I had more examples to show. Let's see. Okay. Wonderful. All right. So this factor right here is quadratic. And this one is repeated linear. Now, technically, you could turn a repeated linear factor into a quadratic factor by squaring it. I wouldn't recommend doing that because it's actually easier to work with a repeated linear factor. So you're going to see that we have a slightly different solution process for this, and we're going to actually have a slightly different way that we're going to use to find the values that we need in our partial fraction expansion. So I'm going to show you how to do some of this work on your calculators. So let's see, we're going to take our integrand out. 4 minus 2x divided by x squared plus 1 times x minus 1 quantity squared. And again, you should recognize this as a partial fractions problem because you have a denominator that's factored. Generally, if you're given a problem and the denominator is already factored, that should be screaming out for you partial fraction expansion. I've seen students do crazy things where they multiply this quantity out, they square it, and then they multiply it by the quadratic, and then they're like, okay, now what do I do? If it's already factored, you should be doing partial fractions. If it's something that's easily factorable, partial fractions. If you can't factor it and it's not already factored, obviously, then you would go to completing the square. These are the kinds of things you should be thinking about. Okay, so you have the quadratic factor that we're going to put first, just because it does not matter the order in which you do this. If you do this in a different order than me, your variables A, B, and C, and D will just end up taking on different or each other's values. For a quadratic factor, remember how I said that the numerator in your partial expansion or your partial fraction expansion always needs to be 1 degree less than the denominator? So this denominator is quadratic, so you want your numerator to be linear. If I want my numerator to be linear, it's going to have to be written in a linear form. If you'll remember, we talked about linear forms right away. We said that a linear form was something in the form of ax plus b. So we're just going to go ahead and use ax plus b. Okay, so make sure that your numerator is 1 degree less than your denominator. Make sure you cover every possible value there as far as I don't want to say place value, every degree. So don't just write ax. Technically, ax is linear, but you need to cover the possibility that there could be some sort of value b as a constant in that expression. Right, now you're going to deal with the repeated linear factors. You have two factors of x minus 1. So you're going to use the first factor with a linear numerator, so you can just use c, and then you're going to use that factor both times it appears with d. Remember, if it's a linear factor, it only needs a constant in the numerator. So yes, technically, if you multiplied it out, it'd be quadratic, but you're thinking of the factor itself, which is linear. This is your setup. If anything gets screwed up on these, it's very likely going to be in the setup. Sometimes students have a hard time with finding A, B, C, and D if they lose something in their work along the way. But usually, if your setup's wrong, everything else is based off that. So just be very methodical about how you set this up. So I'm going to use the same process here to get my fractions cleared. I'm going to multiply every single term by the LCD. So I'm not going to show that work. It's very tedious to show that 4 times, but you can think about this visually. If you multiply this first term by your denominator, x squared plus 1 times x minus 1 quantity squared, well, the x squareds plus 1 are going to cancel, and what you're going to be left with is ax plus b times the quantity x minus 1 squared. And what students start to recognize here is whatever they don't have in the denominator, but they do have over here, is what is going to end up getting multiplied by the function. Then you'll have c. Well, for c, you have one factor of x minus 1 in the denominator. So you're going to multiply that by x squared plus 1 times 1 factor of x minus 1. Everything else would cancel, or technically the 1 factor of x minus 1 would cancel. And then for d, when you multiply d by x squared plus 1 times x minus 1 squared, the x minus 1 squareds are going to cancel, and that just leaves you with x squared plus 1. Okay, so you're looking at this and thinking like, oh, wow, this looks a little bit heftier. And it's true. Let me tell you the big issue that I have with this as far as choosing values for x. Technically, yes, you could go through and say, well, let's let x be 1. If you did that, you could let x be 1. That would affect these two factors right here. And that would zero out a, b, and c, because you'd be multiplying by 0 in that case. And you'd be able to solve for d. However, you're not going to be able to do the same thing to eliminate the other variables. So, I mean, I can't find a number such that when I square it and add 1, I get 0. So I'm not going to be able to zero out this term. And then you're going to be left with all these variables that you're kind of like, okay, well, I've already used that one technique that I have. What's left now? So I'm going to show you another method for doing this. It's called equating coefficients. You can use this all the time if you want. It's just that if you're doing something basic, like what we did with examples 1, 2, and 3, it's actually faster and easier to do it the way we did it in examples 1, 2, and 3. But once you start working with more factors and quadratic factors and things that are getting multiplied in, you might find that this gets very, very messy. And it gets to be hard to work with. And we're going to be using our calculators for this once we simplify it down. So our method is going to be equating coefficients. And the way that we're going to do this is also going to be kind of tedious, so be careful with your work here. But it will involve our calculators once we get to our tapping point at the end. Okay, so what I'm going to do is I'm going to keep the 4 minus 2x on the left. And on the right-hand side, we're going to expand this out. And I know that so far I've said don't expand, leave everything factored. But to equate coefficients, we're going to have to be able to equate the constants and equate the linears, equate the quadratics, so on and so forth. So you're going to have to be very careful with your work. I'm going to first square this quantity. I can't multiply ax plus b into x minus 1 until I square it. And some of you are like, oh my gosh, is this happening? Sorry, it is happening. X minus 1 quantity squared is x minus 1 times itself. So you're going to have to FOIL that. You'll get x squared minus 2x plus 1. And then you can go ahead and multiply these two binomials together. So you'll have x cubed minus x squared plus x minus 1. And we're just going to be doing this in a series of steps. So go ahead and just multiply in whatever you can when you're at that step. Just sort of simplify this down. So I went ahead and distributed the d. In this step, I'm going to multiply the ax plus b into this trinomial. And none of this is calculus. This is all algebra at this point. It's just tedious algebra. So be careful. Watch your steps. So I'm going to first work with the ax on all three terms, and then I'm going to work with the b. So ax times x squared is ax cubed, and then I have minus 2ax squared, and then I have plus ax. And then notice that in each time you're checking just to make sure that each one of these has an a on it, each one of these has an x, and the x are in descending order. Just do a quick double check to make sure that things are happening the way they should be. Now I'm going to work with the b. We have bx squared minus 2bx plus b. Now I'm going to distribute the c into the parentheses. So I have cx cubed minus cx squared plus cx minus c, and then plus dx squared plus d. This is reminding me now of that suggestion that Becky had to flip your paper off to the side. This might be one of those instances where you might find that works better for you, because some of these equations are going to get kind of long, like this. Probably not anything longer than this, but this length is more common. All right, so the whole method of equating coefficients is we want to get all the powers that match together. So I want all the x cubes together, the x squareds together, the x's, and the constants. If you would like, you don't have to, you can rewrite the order of this on the left so that it's descending. You don't have to, but it might be easier if you kept everything descending, but that's totally up to you. All right, I'm going to look for the highest power that I have, which in this case is x cubed. And I'm going to take the x cubed and I'm going to factor it out. And I'm going to take anything that's in that factor and include it in the factor. So I have an ax cubed and a cx cubed. The c is positive. So I'm going to say this is a plus c. So ax cubed plus cx cubed. If you factor out the x cubed, you'll get a plus c. Now I'm going to take the x squareds. I'm trying to go in descending order here. I have a negative 2x squared, a bx squared, a negative cx squared, and a dx squared. So I'm going to take all four of those. So I'm going to just take it out as a positive x squared. Then I'll have negative 2a. Don't take this out as a negative x squared. I know that it looks like negative here. I would just call it x squared. Just group it together that way. All right, negative 2a plus b minus c plus d. And, just about right now, some of you might be thinking like, oh, maybe I should have done this the other way. You'd be surprised. I know this seems tedious, but this way, actually, if you have a really hairy problem, it's probably going to work out better for you in the end. Just, really watch your work. All right, let's take the x's now and be careful not to lose anything. So we have an ax. I have a minus 2bx, cx. I do not have a dx. And then we have constants. You can group them together if you'd like. You don't have to. I don't know. Sometimes I just group them together just so they're obviously standing out. So anything that doesn't have an x on it. So I have a b. These have x's. So minus c plus d. It seemed like it took a long time because I was demonstrating, but when you're doing this on your own, it should not be something that's super crazy. All right, so now I'm going to set up a system of equations. Don't freak out. It's a system of equations equating these coefficients. So what you're going to notice over here on is you're going to match up what you have on the right with what you have on the left. So x cubed, for instance, is on the right. You're going to look over to the left. Do you have any x cubes? No, you don't. You just have x, some sort of linear term, and then you have a constant. But you don't have any x cubes. So these a plus c values have to add up to 0 because you don't have any of that. This is an equation. What you have on the left, you must also have on the right. It's an equation. You don't have an x cubed on the left. So it must be the case that a plus c equals 0. So that's one equation that you're looking at. You're looking then at x squareds. Again, I don't have any x squareds on the left. So I'm going to let the x squared quantity also be 0. So negative 2a, yeah, we'll just write it like this for now, plus b minus c plus d equals 0. Double check to make sure you rewrote it correctly. That'd be terrible if you just copied it down wrong. All right, now for the x's. On the left, I have negative 2. On the right, I have a minus 2b plus c. So instead of setting that equal to 0, I'm going to set it equal to negative 2. And I know I've switched the sides, but there's a reason for that. So if I were you, I would keep it so that the variables are on the left. Now, the last one we have to deal with is the constant. So you do have a constant of 4 on the left-hand side. So we're going to write this as b minus c plus d equals 4. Now you technically have a system of equations, 4 equations with 4 unknowns. That's good though. You should have as many equations as you have unknowns, otherwise you're going to have an issue. And it won't happen because of the way that you set this up. So what you're going to do is you're going to make this look like a system and put it into your calculator. The way I'm going to do this is with a matrix. I'm going to have columns for A, B, C, and D. An augmented matrix. And then I'm going to have the constant on the right-hand side. So for my first equation, I have 1A plus 1C equals 0. So 1A, 1C equals 0. I don't have any B's or D's in this equation, so I'm going to enter B and D as 0. This should be ringing a bell from algebra. But for some of you, it's like, wow, this is like way back in the recesses of my mind. But you did a lot of this in college algebra. The second equation, we have negative 2a plus 1b minus c, so that's negative 1, be careful with that, and then plus d equals 0. For your third equation, you have 1a, negative 2b, 1c, and you have 0 d's, and that's equal to negative 2. And then for your last equation, you have no a's, 1b, negative 1c, 1d, and 4. So I'm going to show you how to do this. I'm going to write down the steps, but I mean, you're right here with me on camera, so you can always rewind it too. But what we're going to do is we're going to, in our calculator, we're going to create RC, rows times columns. So we're going to create a 4 by 5 matrix. We're going to enter in all of these coefficients. And then we're going to go to calculate the RR, EF, to get the solution to the system. There are a bunch of ways of solving systems in your calculator. This is the one that I personally find easiest. And it just involves one matrix and one operation. That's why I feel like this is the best way of doing it. Okay, so you are going to hit, I'm like dealing with absolute daylight here, and I never teach in this light. My kids are all at school right now, so I got to keep my eye on the clock. All right, you're going to hit the matrix menu, which is second, and then X inverse. That'll get you your matrix menu. Oh, okay. You need to choose which matrix you're going to use. All of mine are already filled up. That's fine though. I actually already put this in yesterday just because I planned to do it yesterday, long story. You're going to go to edit, and that's going to allow you to put the coefficients in your matrix. So when you're in here, it'll go under names. If you just hit enter, it's going to take you back to your home screen, and you're going to be like, oh, didn't mean to do that. And then you're going to go back to your matrix menu again. I do that all the time. I accidentally do that. But okay, so go over to edit. There we go. And then you're going to hit enter. Now, I already set mine up as 4x5. I know I should delete this just so that we can redo it. Okay. Yours might be set by default to something else, but the first number is the number of rows. The second number is the number of columns. So we want 4 rows and 5 columns to match our data that we came up with. And you probably forgot what we were even doing at all. What were we doing? We were integrating, and somehow we ended up in the matrix menu of our graphing calculators. You know, it happens. It's once we get there, the integrals themselves are going to be super straightforward. We just need to figure out exactly how we're splitting them up. Okay, so so here we are. I'm going to enter all my coefficients, and the way your calculator is going to do this when you hit enter is it's just going to go left to right, and then it's going to go down to the next row, and it's going to go left to right again. So you're going to be really careful here. 1 0 1 0 0. So 1 0 is already there. 1 0 0, and you're just going to copy this down to match what's on your sheet. So -2 1 -1 1 0. And I'm just hitting enter after I enter each number. 1 enter, -2 1 0 -2. And then for the last row, I have 0 1 -1 1 4. And then I'm going to double check and make sure that all of the entries in my calculator match what's actually on my paper. So -2 1 -1 1 0 1 -2 1 0 -2 0 1 -1 1 4. Okay, we're good. So now you're going to go back into your matrix menu. If you haven't done this in a while, I'm reminding you now. So go back to your matrix menu, which is second X inverse, and you're going to hit the math button. Oh, you know what? I might have to go to the home screen first. Let me see. You're going to scroll up, not down, because you're going to get there faster. And you're going to hit RREF, which is B. Not REF, RREF. Yeah, I needed to go back to my home screen. Okay. Second quit, you got to be in your home screen. Otherwise, it's going to pull your matrix math into wherever you happen to be at that moment. Okay, sorry. Back to your matrix menu. Go to math. Scroll up to RREF. Hit enter. Now it's asking you, okay, you want me to do reduced row echelon form of what? Well, you're just going to enter whatever matrix you just entered in your calculator. So you're going to go back to your matrix menu, and these are just the names. We entered this as matrix A. Just use A, it'll make your life easier. And hit enter. And then it's going to say, all right, we're going to do reduced row echelon form on matrix A. You can close the parenthesis if you want. You don't have to. And you're going to hit enter. What this does is it pops out something called reduced row echelon form, which you should have seen in college algebra. Oh, this is one there. that in. 0, 0, 0, 1, 2, 1, -2, 1. What this is doing is it's reorganizing your matrix using a series of row operations. You hopefully remember doing this where you would take one row and add it to another, and then take another row, multiply it by something, and add it to another row to get a new row. And you were trying to get zeros down here in the lower left-hand corner and the upper right-hand corner, because remember that your columns represent the variables that you're trying to find. So what this really means is 1A equals 2, 1B, so 0A plus 1B plus 0C plus 0D equals 1. So that just means that B equals 1. 1C equals -2. And 1D equals 1. That's what your result means. So when you pop this up, I know that on your calculator, it doesn't give you this vertical bar. That's okay. That's implied. It's there. It's still technically an augmented matrix. The values that you get over here on your rightmost column are going to be the solutions in order A, B, C, D. I mean, assuming that that's the way you set up your system. I don't know why you'd set it up any differently, but who knows? I've never seen a student do anything like that. So even though this was a little bit tedious, your calculator is actually doing the system's work for you. The only work you're doing down here is, you know, basic algebra, just FOILing, combining like terms, factoring. Okay, so anyway, now you're kind of like, okay, fine, A, B, C, D. What was I doing with those again? I'm going to remind you now what we were doing to begin with. We were trying to find these coefficients and constants. We found them. Now we can rewrite the integral. I'm just going to move to the next page. That would make the most sense. Okay, so we will have then the integral of 4 minus 2x divided by x squared plus 1 over x minus 1 quantity squared dx is equal to, I'm going to be looking at the values straight out of my calculator. I know I wrote them, but I can only put so many things on the screen at one time. A is 2, so I have 2x plus b is 1, 2x plus b, 2x plus 1 divided by x squared plus 1, and then plus c, which is -2 divided by x minus 1, and then plus d, which is 1 divided by x minus 1 squared dx. Okay, make sure everybody can see that. Make sure everything's accounted for. All right, looks good. All right, so now we're just at the point, I should probably keep this up here. Just need to reference it. All right, so now we're at the point where we need to start integrating. And then you're going to have to, for some of these, really think about what you need to do to integrate the function. For instance, this one I'm not worried about. The last one, this is just going to be a u substitution with u equals x minus 1. No big deal there. Du is dx. That's what you have. This one is going to be a natural log form. No big deal. Natural log u or natural log w, something like that. This one's the one you need to think about. Now, don't freak out. I know that in this chapter, we've seen denominators that were written in the form u squared plus a squared, and we're just like, oh my gosh, this looks like it's going nowhere good. But actually, this is technically a Calc 1 integral. I think this could be more focused. Okay. So one thing you might want to notice is that if this was just 2x instead of 2x plus 1, you would have something close to du over u. Like, let's say you wanted u. I know I've got a lot of u's going on here. I could call it w, but let's just call it u for a second. Let's say you wanted u to be x squared plus 1, and then du would be 2x dx. Well, you've got a 2x dx already. And if this plus 1 is bothering you, well, don't freak out about it. Just split it off into another integral. So let's rewrite this, because you already know now that, like, okay, this is actually a really nice u substitution without the 1 on it. So I have 2x dx, great. I don't have the plus 1, but that's fine. We'll work on that. So go ahead and split this up now so that you have 2x over x squared plus 1 dx. Split the plus 1 off into a separate term. So you can write it as plus 1, but it's implied. So we'll just write it as dx over x squared plus 1. Then you'll have minus 2 times the integral of dx over x minus 1. That's this one. And then you'll have plus the integral of 1 over x minus 1 squared dx. It's funny, I was just looking at this a few minutes ago and saying, like, oh, I thought I had more examples to prepare. This is like, we're going to be done with this so fast. But I neglected to consider all the work that goes into this and having to explain all the little pieces. All the pieces. Okay. Excellent. So we already pretty much did this work over here. If you want to use you can. I know it's kind of confusing though because we used it over here. So if you're going to do that, you're going to have to keep track of which one's which. But we know in this case we have du over u, and anytime you have du over u, you're looking at a natural log of u. So for the first term, we're going to have the natural log of x squared plus 1. I'm going to drop these bars in a minute. I'm writing them just because I don't want you to forget to write them when they're necessary. In the next step, I'm going to drop them, though, because the quantity x squared plus 1 can never be negative. The reason we use the bars is so that we can force the quantity to be positive. X squared is always going to be positive all the time, or it could technically be 0, but add 1 to it, and it's always going to be positive. So you don't have to force it to be positive. It already is. So it's not a big deal if you use absolute value bars, but I'm going to switch these to parentheses because this is a special case with this expression. All right, this integral, if you don't recognize it, where is it? I was going to go back and show you because we talked about it recently. Oh, yes, here we go. I brought it up at the beginning of 7.4. 7.4, integrands containing ax squared plus bx plus c. There it is. 1 over 1 plus u squared. Oh, I have a dx on that. Yikes, you guys. And this was asynchronous probably too. Terrible. Go fix that in your notes. I think I switched them over to u's. I think I originally had x's, and I just forgot about the u's. Terrible. Okay, anyway, that was confusing. 1 over 1 plus u squared du is the inverse tangent of u plus c. Well, that's exactly what we have here. We have 1 over x squared plus 1 dx. That'll just be the inverse tangent of x. That one should not be super tricky. You don't have anything else on the x. It's not like you have some u squared plus a squared instance where you have other values. If you have u equals x and a equals 1, that's your basic standard inverse tangent in this form. All right, so this one's your natural log. So you have another natural log. So if u is x plus 1, du is dx, you'll have -2 natural log. These absolute value bars are absolutely required because x could be negative and you're not squaring it in this case. And plus you're subtracting 1, not adding 1. So even if you had x squared minus 1, you'd still need the absolute value bars. It's the x squared plus 1 here that takes it into always positive territory. Now for this one, this is actually the Calc 1 integral. Well, officially they're all Calc 1 integrals, but this is just your basic u substitution. If you let u be x minus 1, then you'll have du equals dx. And then what you'll end up with is just the integral, let me put it right here, of u to the negative second du, which we just did something like that on the previous example. So you're going to take u to the negative first, and then you're going to multiply by or divide by your new exponent, which is -1. And then plus c. So this is what I mean with partial fractions, and that the integrals themselves are not the hard part. Every single integral here is a Calc 1 integral. You learned how to do all of them in Calc 1. It was just rewriting your original. So we took this integral that you originally had and split it up into these 4 Calc 1 integrals. Really, you were just trying to figure out, like, what's the best way to do that? What are the coefficients supposed to be? What values are supposed to be included? And, you know, keep in mind that you can't just be like, well, I don't know what the coefficients are, so I'm just going to call them whatever, and at least my integral will be of the right form, because that might not necessarily be the case. Sometimes you're going to get values of a, b, c, and d that are 0. So you might not have even had one of these terms in your actual integral once you got done with that. It's only in this particular example that you actually had a, b, and c, and d all non-zero values. So don't just make up coefficients and say, well, I know it's of this form, because, I mean, technically you could have d equals 0 and you wouldn't even have this term. Does that make sense? So it is very important that you run through and figure out what all of your coefficients are. It's necessary. Oh, another one. Okay, so officially I have 2 more examples. I don't know if I'm going to get through both of them before I have to go pick up my little one. Those people hate me probably because I'm always late. All right. I don't think they need 3 minutes to pick up your kid is that late, by the way. I mean, it's like 3 minutes. I think it's fine. Okay. We're going to do one with a repeated quadratic factor. Yes. Yes. This will be example 5. Right, example 5. Yes, okay. Wonderful. We're going to do dx divided by x times x squared plus 1 quantity squared. I almost put another dx on that. Crazy. Okay, so again, you're looking at this. There should not be this major debate about, holy cow, what method should I use here? Yeah, officially, you could do a trig substitution because you do have a u squared plus a squared in here, but I mean, I think that's the harder way to go about this personally. But you know, you do you. Okay. So we're already factored. It's got a factored polynomial denominator. You should be thinking partial fractions. Let's go ahead and set this up. So you'll have, officially in the numerator, you have a 1. And you have x times x squared plus 1 squared. So you have a quadratic factor that's repeated. So you're going to use the same process that you would for a repeated linear, except this time you need to make sure your numerators are linear and not constant. So if you want, go ahead and start out with just the x. I tend to just go in order from left to right. So a over x, no big deal there. Then you have one factor of your quadratic factor, x squared plus 1. And the numerator needs to be linear. So we'll call that bx plus c. And then you're going to use the two factors of your repeated quadratic factor. And again, you just need a linear numerator. So dx plus e. If you're going to use e, that's fine. I know sometimes in math they say don't use e as a variable, but that's just because e is also a transcendental number. So if you feel comfortable using e, that's fine. I tend to just leave it as capital E so it doesn't get confusing. If you're going to use d, make sure it doesn't look like a 0. But you know, these are just variables we don't usually work with. So just, you know, watch out for that. Okay, so this is the setup. So here's your linear, your one factor of the quadratic, your repeated quadratic factor. All right, so your linear denominator gets a constant numerator, your quadratic denominators get linear numerators. So there's a lot going on again here. Let's go ahead and set this up. The nice thing, I guess, is that you only have a 1 on the left-hand side, so you're not going to need to use like a whole lot of crazy values here. I mean, it's really with the method we're using, I guess it doesn't really matter anyway. And then we're going to go ahead and multiply through each term by this LCD. When you multiply a over x by your LCD, the x's are going to cancel, and that's going to leave you with a times x squared plus 1 squared. If you want to just write that squared by multiplying it by itself, you might find that that's going to save you a step later. And that's just my suggestion. Then you'll have bx plus c. Don't forget your parentheses. Actually, this is a place where students tend to get their math wrong because they don't put parentheses around this binomial, and then it doesn't get distributed into what comes behind it. So both of these terms need to get multiplied by, well, if you multiply it by the LCD, you're going to have an x and then one factor of x squared plus 1. Just, you know, use grouping symbols as liberally as you need to. Now, when you multiply your LCD by the last term, both factors of x squared plus 1 are going to cancel out, and that's just going to leave you with an x. So you're going to have dx plus e times x. I'm trying to be very methodical about just keeping the same form as I work my way through, so that you get very used to just kind of doing these the same way. So this is what it looks like. Anytime I've got a whole bunch of quadratic factors in the denominator and linear factors in the numerator, I tend to equate coefficients. I mean, if you were trying to do this by just saying, oh, well, let's let x equal 0. I mean, yeah, you could isolate a variable here and there. You could get a pretty quickly if you let x be 0, but then you'd have a really hard time getting the other ones. So I'm going to do this method again of equating coefficients. However, if you feel like you would be able to solve this system without it, that's fine. I just think this is usually the way that you do this when you have a little bit more of a complicated equation. So we're going to go through, same idea here. I'm going to multiply through. I'm going to have x to the 4th plus 2x squared plus 1 plus, and then if you want to do this all in one felt swoop, fine. If you don't feel comfortable, also fine. I'm going to multiply the x in first to get x cubed plus x. And then we'll have dx squared plus ex. And then I'm going to multiply through again. So this time I'm going to multiply the a in. So I have ax to the 4th plus 2ax squared plus a. And then I'm going to FOIL here in the next group of factors. So I'm going to have bx to the 4th. And then plus, if you want to do cx cubed first, that's fine. Plus bx squared, I just like to have mine in descending order, plus cx. So we did bx times x cubed plus c times x cubed plus bx times x plus c times x, and then plus dx squared plus ex. And now you're ready to just group these according to their number of factors. So I have x to the fourth as my largest one. Like I said, trying to be very methodical about this. So I'm going to gather all the x to the fourths first. I have a, and I have plus b. Now I'm going to look at my x cubes. I have cx cubed. If you want to write it like that, fine. Since you only have one of them, you can just write it as cx cubed, but I don't know. I'm going to be methodical here. I'm going to go to my x squareds. I've got 2a plus b plus d. I'm going to go to the x's now. Don't lose any of your powers of x. So this one's a constant. I just have a cx and an ex. So I'm going to say c plus e. And then for my constants, I only have one constant. That's just this a. Everything else has an x on it. Now, remember at the beginning, I said like, oh, if you start out by letting x be 0, you could solve for a pretty easily. Well, you would have gotten a equals 1, which is the same exact thing you're going to get here. You have a constant a equals your constant 1. So that's one that would have popped out quickly for you. The other ones would be a little bit more work, but I'm just going to set up my system here the way that I did last time. So as far as x to the fourths, you don't have any of them on the left-hand side. So I'm going to say that a plus b equals 0. For your x cubes, you don't have any on the left-hand side. So you would have c equals 0. That's kind of nice. For your x squareds, you don't have any on the left side. So you'll have 2a plus b plus d equals 0. You don't have any x's on the left-hand side. So you have c plus e equals 0. And a, your constant, well, you have one constant on the left-hand side. So we have a equals 1. Now, if you feel like at this point you can do this, that's fine, because you might not need to put this into your calculator. I mean, think about it. If a is 1, and you know that a plus b equals 0, then it must be that b equals -1. So I would say, put it in your calculator if you want to, set up a system if you want to, but if it's something basic like this, you might not want to. Once you kind of see it in this form, well, you can start here, and then you can say, all right, we'll find a is 1, 1 plus b is 0, so therefore b equals -1. Fine. A is +1. If we know that c is 0, and we know that c plus e is 0, then we can use that over here to find that e is 0. And then you already know a and b because you know that a is 1 and b is -1. And you can use that to solve for d. So a is 1, b is -1. You'll have 2 minus 1 plus d equals 0. 2 minus 1 is 1. And then subtract 1 from both sides, and you'll get d equals -1. So it was really nice that we were able to do this by equating coefficients. This would have been a lot harder to solve had we not done that. You would still have used the same amount of space. You probably would have been doing a lot more guesswork, whereas this involved no guessing. We got through here, we came up with some equations, and in this case, our equations were straightforward enough that we were able to solve for some variables. And if you're wondering, like, well, why didn't we do that on the last problem? We didn't have that situation on the last problem. I mean, yeah, maybe some of you could have figured this out, but it's much faster to put it in your calculator. I mean, because A and C could literally be anything. As long as they were opposites, you could add them and they'd equal 0. And then, I mean, you would have had a really hard time doing this without your calculator. I don't know, probably would have been a lot of guesswork. but this was a little bit more straightforward. Okay, so let me zoom out a little bit. Okay, so I want to rewrite our integral using our new coefficients. So we're going to take our integral dx over x times x squared plus 1 quantity squared, and we're going to write it as the integral of a over x, so 1 over x, plus bx plus c. I mean, I'm writing this just because I'm demonstrating it to you. Obviously, you don't have to write a plus 0. So plus bx plus c over x squared plus 1, then plus dx plus e divided by x squared plus 1 quantity squared. And I'm going to, of course, rewrite this again so it's very clear what we're dealing with. And notice that even though you have negative x's in both of these numerators, the denominators are different. But similar types of situations there. But, you know, again, we're just dealing with some calculus integrals. No big deal. So we have the integral of 1 over x dx minus the integral of x over x squared plus 1 dx. I'm just taking this negative x and writing it as minus the integral of x over the quantity x squared plus 1 squared dx. All right. This is just your standard natural log of x, no big deal there. Here you can let u be x squared plus 1. Notice this is not an inverse tangent integral because you have an x in the numerator, not a constant. So if this was a constant over x squared plus 1, you'd be in the form of an inverse tangent, but it's not. This is your numerator being 1 degree less than your denominator. Du is 2x dx. 1/2 du is x dx, which is what you have. And since I used a u substitution here, I'm going to do a w substitution here. W is x squared plus 1. dw is 2x dx. You know I love dw. 1/2 dw is x dx, which is what you have in your numerator. All right, so we have the natural log of the absolute value of x for your first integral. Then you have minus 1/2 times the integral of du over u. And then you have minus, again, 1/2 times the integral of dw over w squared. So if you want to rewrite that as w to the negative second dw, it's probably going to benefit you the most. And you will integrate. So you'll have minus 1/2 ln absolute value of u minus 1/2 w to the negative first divided by -1 plus c. You're going to get used to doing this integral all the time, by the way. It's going to pop up so much in partial fractions that you're going to see this, and you're automatically going to write it as -1 over w, and that's fine. You're going to see it a lot. No need to reinvent the wheel every time. Okay, so this is that special case where you have x squared plus 1. If you want to include the bars, fine. You don't have to, though. It's redundant. 1 over 2, and then w was x squared plus 1 plus c. So I don't know. I'll just write parentheses. I think in the last problem I said I was going to rewrite it with parentheses, and I forgot to. Sorry. I mean, it doesn't matter. It's fine. But this is officially your integral. So we started out up here with a linear factor and a repeated quadratic, set it up as such, and then we just kind of multiplied through each term to clear the fraction using the LCD. We equated coefficients. We luckily had some situations where we were easily able to solve for those variables, substituted back into our original integral, and then we had a series of Calc 1 integrals that we were able to evaluate using natural log and U substitutions. All right, I have one more example, and I still have 25 minutes before pickup. This is amazing. I know it does seem like I go through these a little bit faster on the video, but my aim is always to have the video be a little shorter than a regular class session, and then it gives you time to pause the video if you need to, and you know, kind of catch up if you need to rewind it if you need to. But it doesn't make as much sense for me to build in all these little breaks where I'm like staring at you and being like, any questions? Because I'll just be talking to myself like I am right now. All right, so last example. The last one is the best one, always, especially in this case. Figure out where I put it. There we go. All right. This will be, guess I'll keep it on the same page. Why not? We've got space. Example 6. This is the integral of 7x squared minus 13x plus 13 divided by x minus 2 times x squared minus 2x plus 3 dx. Now, if you're wondering, like, oh, well, why didn't she factor this? Well, take a look at the signs. You can't think of any two numbers that multiply to give you positive 3 and add to give you negative 2. So be careful here. Don't do something dumb and factor this incorrectly and then just have 3 linear factors and you'll be like, okay, done, 3 natural log functions, because that's not actually what you have here. This is a linear factor. This is a quadratic factor. It's not factorable. You can't find two numbers that multiply to give you positive 3 and add to give you negative 2. It'd have to be negative 3 and negative 1, but those add to negative 4. So if this was negative 3, you'd have a different situation here, but it is not. Alas, you are stuck with what you have. So let's go ahead and set this up. 7x squared minus 13x plus 13 divided by x minus 2 times x squared minus 2x plus 3 equals, then we have a over x minus 2, and then here's your quadratic factor, but it's not repeated. So the numerator is going to be bx plus c, and then divided by x squared minus 2x plus 3. So you're like, why is this the last example? It's just got A, B, and C in it. No big deal. Well, I mean, it's not that big of a deal. I mean, it all depends on what you find to be a big deal. Okay. If you're guessing, why is this problem number 6? Think about what happens here if we get values for B and C that are non-zero. You're going to have to evaluate this integral. These are the things I want you thinking about. What are you going to do here to evaluate this? The denominator is not factorable. What do we do when the denominator is not factorable? So I'm just trying to plant the seeds right now. Okay, but for now, let's focus on what we can do. And what we can do is go ahead and set up our partial fraction expansion. Oh, and by the way, even though, yeah, technically I'm trying to plant the seeds for this term, as it is given to you in this form, anytime you're looking at an example where you're being asked to integrate and you've got a factored polynomial in the denominator, partial fractions every time. Okay. A times your other factor, x squared, why do I keep writing that as plus? minus 2x plus 3 plus, don't forget your parentheses, bx plus c times the quantity x minus 2. If you want to try the method of letting x be this, letting x be that, that's fine. You still might end up with a system of equations you'll have to solve, but I'm going to just equate coefficients because this is not going to be too crazy to do over here. And I thought maybe having one more example of putting this in your calculator would be helpful. Ax squared minus 2ax plus 3a plus, here we've got bx squared minus 2bx plus cx minus 2c. And I know I'm going through this a little bit quickly just because it's your algebra, but be careful here. This is where a lot of little mistakes happen and they have a big effect. All right, I'm going to now set the powers of x together. I'm going to put them together. The highest power I have is x squared. Well, I have an ax squared and a bx squared. So I have a plus b. Then I have for x's negative 2a minus 2b plus c. And then for my constants, I have a 3a that doesn't have an x on it, so it's a constant, and a minus 2c. And again, these don't have to have parentheses around them. I just kind of like to have everything grouped, so I tend to put parentheses around them regardless. Let's see if I can focus this even better. I swear it looks different depending on whether it's on Google Meet or on my application. That's good as it's going to get. Okay. Wonderful. So let's go ahead and equate the coefficients. I know that for the x squared, I have 7 equals a plus b. So I'm going to go ahead and use that. A plus b equals 7. Then I have negative 13 equals negative 2a minus 2b plus c. So minus 2a minus 2b plus c equals negative 13. There's a minus sign in front of it. Just, make sure all those little things are accounted for. Those are your x's. And then for your constants, you have 3a minus 2c equals positive 13. Now, this is one where you're going to have a much harder time doing this by hand. So I guess you could technically put these together and pop it in there. Just do it on your calculator. I'm not testing you here over your ability to solve systems of equations unless it's how you enter it in your calculator. So let's go ahead and set up a matrix where we have A, B, and C. We're going to have 3 equations, 3 unknowns. A plus B plus 0C is 7. So that's your first equation. A, 1A plus 1B, no C's equals 7. Then you'll have negative 2a minus 2b plus 1c equals negative 13. And then 3a plus 0b minus 2c equals positive 13. And we will go through and put this into our calculators and get a solution. Now, this time, if you don't want to use A, that's fine. I tend to just always use A. It just makes my life easier. So I'm going to go back into the matrix menu. I'm going to edit. So scroll to the right to edit, and I'm just going to hit enter. And instead of a 4x5, remember this is rows by columns. I have 3 rows, 4 columns. And that's what this is going to look like. And you can just go over the numbers that you have. 1, 1, 0, 7. Being careful. Negative 2, negative 2, 1, negative 13. 3, 0, negative 2, 13. And then you're going to double check. I know I keep saying that because it's crucial that this matches. Okay, 1, 1, 0, 7, negative 2, negative 2, 1, negative 13, 3, 0, negative 2, 13. Awesome. Okay, now you're going to go to your home screen, so second quit. And if you want, pull up the function you just used by using second entry. If you don't want to do that, I'll remind you, you hit the matrix menu, scroll over to math, go up to RREF and hit enter, and then go back again and pick up matrix A. And then your solution is 5, 2, 1. Okay, so A equals 5, B equals 2, C equals 1. I'm not going to write this whole crazy matrix down. Doesn't matter. All we're looking for are the quantities A, B, and C, which we now have, A, B, C. And whatever order you put them in, that's what they're going to be down here. 5, 2, 1. All right, now we're going to go ahead and put this integral back together. Oh, you guys, I'm getting excited. You know I love this stuff. Love it. Oh, I do. I can't help it. I don't know what's wrong with me. Okay, A over x minus 2. So, sorry, I know this is going to be a little bit hard to see here. There's got to be a faster way of doing this, but there we go. Okay, so A over x minus 2 is 5 over x minus 2. I'm just going to go ahead and split this off into its own term. Plus bx plus c, so 2x plus 1 divided by x squared minus 2x plus 3 dx. Okay, now, there's that. If this is bugging you, if you're kind of like, you can always test it out. This, I'm not worried about this integral. This is a natural log, no big deal. 5 times the integral of 1 over x minus 2 dx, natural log. I'm mostly worried about this one. So this one is your log form, no big deal. This one I'm worried about. Let's say you wanted to try to fit it into a log form. I'm reminding you what we've been doing for the last, like, I don't know, week or so. You do that by saying, no, let's try this. We'll let u be the denominator. This was the technique that we used. I've done this a few times now, so I hope you're getting used to it. Well, then du is 2x minus 2 dx, if it's going to fit into your natural log form. Well, we are going to force it to happen. Okay, so let's force this here. I'm going to hold off on this. I'm going to say come back. Don't forget about it. But for right now, I'm going to head over here. I'm going to rewrite this integral as 2x minus 2, because that's what I need there, divided by x squared minus 2x plus 3 dx. That's a natural log, du over u. Fine. But we had a plus 1. 2x, sorry, I'm going to force this to be the way that it is. 2x minus 2 plus 2 plus 1. So this was what we created. We made it into 2x minus 2, but when you subtract 2, you have to then add 2. And you originally had a plus 1. So this turns into 2x minus 2 plus 3. So your second integral is going to be plus 3 times the integral of, you know what, I'm going to just write it together right now because I don't want it to look confusing. 3 divided by x squared minus 2x plus 3 dx. Okay, so that is this integral. So there's a lot going on here. Don't forget about this. We've taken this integral and we've split it up into these two terms. This is a natural log form. No big deal. Come back. So we've got 2 natural logs that we have to come back for and pick up. We're going to focus on this one. That is not a natural log. And if you're wondering what the heck is it, well, it's currently not in a natural log form. It's not factorable, so I can't use partial fractions on it. I already used partial fractions just to get here to begin with. So what we're going to have to do is complete the square. That's fine though. We've done this a lot. Half of 2 is 1. Square it and you still get 1. When you add 1, you must also subtract it. So this will be x minus 1 quantity squared plus 2. This is what you do when you don't have a natural log form. In most cases, you're going to see a quadratic denominator and a constant numerator. You can't factor it. You complete the square. So we're going to take 3 divided by x squared minus 2x plus 3 dx, and we're going to rewrite it as the integral of 3 divided by x minus 1 quantity squared plus 2 dx. And then you still have options, because this could technically be fit into an inverse tangent form. It is a constant divided by u squared plus a squared. Remember, your inverse tangent form doesn't have a radical. You can do that, or you can force this into a trig substitution where you have this quantity under a radical being squared. You can do that also. It's kind of up to you. How do I want to do this? Honestly, I was planning on doing a trig substitution, but now I kind of want to fit this into an inverse tangent form. I feel like it's more obvious that way. So I'm going to write can do trig sub with x minus 1 squared plus 2 being the square root of x minus 1 squared plus 2 squared, or use inverse tan form. That's what I'm going to do. Okay, so I know that the integral of du over 1 plus u squared is the inverse tangent of u plus c. So this is your recall. That's what we're going to go for. The 3 we can move to the outside. If it's bugging you, which it's kind of bugging me, I'm actually just going to pop it onto the outside here so we don't need to worry about it. We're going to end up manipulating this anyway, so no big deal. Okay. Let's see. So we're going to have, in this case, we're going for u squared plus 1. I don't have a 1 though, I have a 2. So I'm going to take my integral and I'm going to divide everywhere by 2. So every term, I'm going to divide by 2. 2 divided by 2 gives me 1. This is good. We haven't done this in a few days, so this is good. I'm going to pull the 1/2 out front. And then remember that if I want this entire quantity to be squared, I need to also square root the denominator so that I can then square it. So I'm going to go ahead and say this is x minus 1 divided by the square root of 2 quantity squared. And now I haven't changed it. I've just rewritten it so that the whole fraction is being squared and not just the numerator. So we did this in 7.4 in the first couple of examples. We did some of these. Well, now you're in the form that you need. You have 1 plus u squared, and then we just need to force our du here. So we're going to say that u equals x minus 1 divided by the square root of 2. If that looks weird to you, you can write it as 1 over the square root of 2 times the quantity x minus 1. And if you want to even distribute that in, you can. Du is going to be 1 over the square root of 2 dx. And then if you're trying to get dx by itself, well, the square root of 2 du equals dx. Okay, so going back here, we have 3 halves times the integral of the square root of 2 du. So pulling that back in for our dx divided by u squared plus 1. And this will be 3 times the square root of 2 over 2 times the inverse tangent of u plus c. And now we can pull all of this back in together. U was x minus 1 over the square root of 2. Go back and get your other 2 integrals. One of them, see if I can zoom all the way back out. I can only go so far. One of them was up here, 5 over x minus 2 dx. So we have 5 times the natural log of x minus 2. That covers this integral. And then we said this was your other natural log form, no big deal. You already did the work for it. You said that u was the denominator, du was 2x minus 2. You rewrote it so that you had du over u. So that's just going to be the natural log of u. So plus ln absolute value x squared minus 2x plus 3 for that integral. That one right there. Just the integral of du over u is ln u plus c. And then for your last one, well, we just found that. I can only go so far back. This one. So we took the 3, we put it out front, we included it here. So you also have plus 3 root 2 over 2 times the inverse tangent of x minus 1 over the square root of 2 plus c. All right. Gosh, you guys, this is good stuff. This is awesome. I'm really happy. You know, I still have like 5 minutes before I even have to leave to pick up my 2-year-old. This is amazing. All right, so we started out, we had something that was factored. We said if you have a factored polynomial denominator, partial fractions. So we split that up. We had a linear factor, we had a quadratic factor. That means constant numerator, linear numerator. Then we went through, we did our equating coefficients. We said, this doesn't look super obvious. So we went ahead and set up a matrix to solve the system. We got A, B, and C. Once we found those, we used A, B, and C to rewrite the integral, which was somewhere. I lost it. There, there it is. All right. So we had A, B, and C. We used A, B, and C to rewrite the integral. Then we said, okay, this one, no big deal, natural log. This one looks natural log-ish. We might have an issue here. We might have to force it. So we did. We checked it out. We said, let's let u be the denominator. Du has to be 2x minus 2. We made it that way. We said, all right, if we're going to create 2x minus 2, we need to also add 2. So you had 2x minus 2 plus 3. So then we said, no big deal, natural log form. Got it. This was the last one we needed to work on. We used a process that we used back in the beginning of section 7.4, where we went ahead and completed the square, wrote this in the form u squared plus a squared, got it looking like this. We had some options here. We could have done a trig substitution. If you wanted to go back and try it that way, that's fine. Feel free. Most students, if they don't have to do a trig substitution, they don't want to. It turns into like square root 2 secant squared theta d theta divided by 2 secant squared theta. If you were looking at that, I can always go through that with you if you would like. But you can use that if you would like. I did the inverse tangent form, which I know some people don't like to do this because they find it complicated. But is it really more complicated than a trig substitution? Probably not. We just matched up the forms. So we said, all right, we want this to be a 1. Got it. We divided every term by 2. made this into a quantity squared, set this equal to our u, and then just integrated our way through. All right. Excellent. This is great. That was all I had to say for 7.5. I did say I was going to put up a review assignment, which is the mixed practice from 7.9, but I'm not going to have that due until like right before your test. So I'm going to give you some time to work on it, but it is going to be a really good idea for you to start synthesizing all this information. Hopefully you saw even more of this synthesis today where you're able to put together some different methods in order to actually, integrate different types of functions. You get used to seeing different types of things here. I'm also going to put up a 7.5 assignment for you guys as well. Email me if you have questions. Also, the office hour on Mondays is still available at 5 p.m. It hasn't been very busy. I've had like 2 people in there. One time I had nobody. But come in for the Monday office hour. It's much easier to ask your questions in person than it is to email them to me. I get if you're emailing me in between, that's fine. But if you're available Monday for the office hour, you might be the only one in there, and you'll have my full attention, and it's a little bit easier to show things instead of type them out. So anyway, I hope you guys have a great week, and I'll see you Wednesday. Okay. Wonderful. Enjoy doing your math. I really enjoyed it. This was a really nice addition to my morning. I should do this more often. All right.